To start with then, pause the slides and use the graph here to explain why the melting and boiling point increases across metals, why silicon has the highest melting and boiling points, and why phosphorus has a lower melting and boiling point than sulfur. So pause and have a go at those. So firstly, why does the melting and boiling points increase across the metals? The reason is the size of the ions decreases across the period. Meanwhile, the charge on the ions increases. That means that the attraction between the ions and the delocalized electrons increases, and therefore more energy is required to separate them. Why silicon has the highest melting and boiling point, you need to think about what its bonding and structure are. So it is giant covalent. Every silicon atom is attached to 4 others by covalent bonds. These covalent bonds are very strong. So essentially you've got many strong covalent bonds. So lots of energy is needed to break them. Why is phosphorus having a lower melting and boiling point than sulfur? Again, you need to go to structure and bonding and think about size of molecules. So phosphorus is P4, where sulfur is S8. That means that there's a bigger surface area or more electrons in S8. So there are more or stronger van der Waals forces, and therefore you need more energy to overcome them. That links us nicely into the topic in this lecture, which is the properties of period 3 elements and their oxides. What you need to be able to do is describe the reactions of sodium and magnesium with water. You state how the elements from sodium to sulfur react with oxygen, and then describe the physical properties of the oxides of sodium to sulfur and their reactions with water. So we are focusing on period 3 in this lecture. So the elements of period 3 are shown here. So on the left, you've got your metals. Silicon there is called a metalloid. It's a semi-metal. It's somewhere in the middle. You then got your non-metals, phosphorus, sulfur, and chlorine. And then argon, which is a non-metal but also a noble gas. Sodium and magnesium are the only period 3 metals that will react with cold water. The reactions of sodium and magnesium with cold water are redox reactions, and we're going to look at that now and look into how we know. So this is the equation for the reaction of sodium metal with water to form sodium hydroxide and hydrogen. Now, if you were to do this reaction, you would see that it is very, very vigorous. You will probably have seen it before where your teacher's thrown some into a big trough of water, and you see that the sodium floats and it sort of fizzes and whizzes around on the surface. They may then have also put universal indicator into the trough afterwards, and you'll have seen that there is an alkaline solution has formed. The alkaline solution was the sodium hydroxide solution. Now this is actually a redox reaction. So if we work out the oxidation states of each of these species, we will be able to show this. So sodium on the left there is uncombined. It is oxidation state 0. You've got water, you've got the hydrogen +1 and the oxygen -2. Remembering that for oxidation states, you give the oxidation state per element, not the overall one from all of the elements. So you give it for each individual one. So each hydrogen is +1. On the right hand side, sodium is now +1, oxygen is still -2, and that particular hydrogen is +1. Then we've also got hydrogen on the far right here in oxidation state 0. So that means that the sodium has gone from 0 to +1. So it has lost electrons, it's been oxidized, whereas 2 of the hydrogens have gained electrons, so they have been reduced. So it is a redox reaction. This equation shows a reaction of magnesium with cold water. Now this is a much slower reaction. It's a very, very slow reaction. You might remember that from doing group 2 in year 1 of the course. So it's very, very slow at room temperature. We will look at what happens if you heat up in a minute. The solution that's formed is less alkaline, pH of around 10, and that's because the magnesium hydroxide is not as soluble, so there's less free hydroxide, which brings the pH down. In terms of oxidation states, top left there, magnesium is 0. In water, the hydrogen is +1, and the oxygen's -2. On the right hand side, magnesium is now +2, oxygen still -2, and that particular hydrogen +1. But hydrogen on the far right over there again is 0. So that means that your magnesium has gone up in oxidation state, it has lost electrons, so it has been oxidized, and again it's hydrogen that has been reduced in that reaction. I said we'd come back to what happens if it's hot. So if you react magnesium with hot water, so steam, you will make magnesium oxide instead. Again, this is a redox reaction. The oxidation state of the magnesium on the left is 0. The water, you've got hydrogen at +1 and oxygen at -2. And then the magnesium on the right is +2, oxygen -2, and hydrogen 0. So again, the magnesium has been oxidized and the hydrogen has been reduced. So it is much faster with steam, but it is a different product. You must note that different product that's formed, magnesium oxide rather than magnesium hydroxide. Moving on then to reactions with oxygen, all period 3 elements, except for argon, which is the noble gas, all period 3 elements are relatively reactive. You can prepare the oxides of the period 3 elements by direct reaction of the elements with elemental oxygen, so just reacting it with O2. All of the reactions, so all of the reactions of the period 3 elements with oxygen are exothermic. Starting with sodium then, here's the equation for the reaction of sodium with oxygen to form sodium oxide. This burns with a bright yellow flame, and you do need to learn the equations, and you need to know the flame colours for these reactions. So you must learn those flame colours. Looking at oxidation states again, sodium on the left there is oxidation state 0, it's uncombined, as is oxygen, so this is also 0. And on the right, we've got sodium at +1 and oxygen at -2. So oxygen has gone from 0 to -2. It has gained electrons, it has been reduced, and the sodium has gone from 0 to +1, so it's lost electrons, it has been oxidized. Here's a reaction for magnesium with oxygen. So this burns with a bright white flame. You will likely have seen this when you've put strips of magnesium in the Bunsen and you're probably told not to look at it directly. It burns with a very, very bright white flame. It produces a white powder of magnesium oxide. Again, let's look at oxidation states. So magnesium, 0 on the left, oxygen 0. On the right, we've got magnesium at +2 and oxygen at -2. So again, the oxygen has been reduced, and this time magnesium has been oxidized. Aluminium then. Aluminium reacts with oxygen in this equation shown below to make aluminium oxide. This is also with a bright white flame and also produces a white powder of aluminium oxide. Now, aluminium itself, the metal, is quite often coated with a layer of aluminium oxide. So aluminium metal itself is actually quite reactive, but this layer of oxide on its surface makes it look like it's unreactive. It's got lots and lots of everyday uses. It's not that it itself is unreactive, it's just that it's coated in this layer of aluminium oxide. So even when scratched, the exposed surface reacts very, very quickly, and that layer covers it back over again. So you've got this layer of aluminium oxide on the outside, and that is what protects it and what makes it look like it's unreactive. Again, oxidation states, aluminium 0, oxygen 0. On the right, aluminium's +3 and oxygen -2. So again, the oxygen has been reduced and the aluminium has been oxidized. So silicon then. Silicon is quite unreactive. It will form the oxide if you heat it strongly enough. So it will form silicon dioxide if you really, really do heat it. Silicon dioxide is a giant covalent substance. So you've got the equation there. Again, silicon, oxidation state 0, oxygen 0. Then silicon becomes +4 and oxygen -2. So the oxygen is reduced and the silicon is oxidized. Phosphorus is a little bit more complicated. So there are two allotropes of phosphorus, red and white. So an allotrope is just different sort of structures of the same element. So for example, graphite and diamond are allotropes of carbon, same element, but the structure is different. So in diamond, obviously carbon forms 4 bonds. In graphite, it forms the 3 with that delocalized layer of electrons between the layers of carbon atoms. So they are allotropes of carbon in the same way that these two allotropes of phosphorus are the same element with different structure. So the allotropes of phosphorus are red and white phosphorus. Now, red phosphorus is not very reactive. It's got to be heated in order for it to react. However, white phosphorus spontaneously ignites, so it is very, very reactive. This gives off a white smoke of phosphorus pentoxide, P4O10. You can also form P2O3 if you have a limited supply of oxygen. So if you're ever asked for an equation in limited supply of oxygen with phosphorus, it's P2O3 that you are forming. Again, oxidation states, phosphorus 0, oxygen will be 0. Phosphorus in the phosphorus pentoxide is +5, and the oxygen is -2. So the phosphorus has been oxidized, and again, oxygen has been reduced. Sulfur then. Sulfur reacts with oxygen to make sulfur dioxide. This is a blue flame that will be seen. So when you burn sulfur, you get a blue flame. You must learn that. There is a little picture there that shows you. You can't see it very clearly, but it is blue. It produces colourless sulfur dioxide gas, as well as some sulfur trioxide. So you'll get a colourless gas. Oxidation states then, sulfur is 0, oxygen 0. Over here we've got sulfur at +4 and oxygen at -2. So the sulfur is oxidized and the oxygen is reduced. Okay, the next thing we need to look at is the trends in melting points of the period 3 oxides we have just been making. So you've got a graph here that shows the melting points for these period 3 oxides. So you've got your metal oxides on the left, the sodium oxide, the magnesium oxide. On the right, you've got your non-metal oxides, silicon oxide, phosphorus pentoxide, and there we've got sulfur trioxide. In the middle, you've got aluminium oxide, and we'll come to why that is not classed as either metal oxide or non-metal oxide. So your metal oxides, your magnesium oxide and your sodium oxide, they are giant ionic lattices. So they have high melting points because of the strong electrostatic forces of attraction between the oppositely charged ions. I said we come to aluminium oxide. Aluminium is a metal. However, in the aluminium oxide, there is an element of covalent character. So what you get is somewhere in between pure ionic bonding and a little bit of covalency in there. And that actually lowers the melting point. So aluminium oxide is sort of the boundary between the ionic bonding and covalent bonding. So you get this strange situation where it's significantly lower because there's a degree of covalent character. So if you're asked about why there is a dip in the aluminium oxide melting point, when you'd actually would expect it to be higher if it was purely ionic, the reason that it's lower than we expect is because of some covalent character, and that lowers it. So that's your metal oxides, and then the aluminum oxide and why that is lower. Let's have a look at the non-metal oxides then. So let's start with silicon dioxide. This has a giant covalent structure. So this has a very, very high melting and boiling point, and because there are many strong covalent bonds that need to be broken, so that'll take a lot of energy, so you can have a high melting point. From there onwards, the melting points are going to decrease. So silicon dioxide is the highest, it's giant covalent, so that's why it's got a very, very high melting point. Looking at oxides of phosphorus and sulfur then, these are simple molecular or covalently bonded molecules. So in between those molecules, we've only got weak intermolecular forces. We've got dipole-dipole and we've got van der Waals, both of which are very, very weak. So there's not going to be a lot of energy needed to overcome those weak intermolecular forces. So they have much lower melting and boiling points. Within that, we need to look at trends between these phosphorus and sulfur oxides. So let's have a look at that. So we can see that phosphorus pentoxide is greater than sulfur trioxide, and sulfur trioxide is greater than sulfur dioxide. That is because of the size of the molecules. So smaller the molecule, the fewer forces there are to break. So sulfur dioxide is the smallest molecule, it has the smallest surface area, so there's less room for van der Waals and dipole-dipole, so you'll need less energy to overcome those forces, so the melting and boiling points are lower. Okay, so we've looked at the period 3 oxides in terms of their melting points. What we now want to do is look at the period 3 oxides with water. Again, I'm going to break them up into 3 sections. I'm going to have my metal oxides, my non-metal oxides, and then some in the middle. So let's start with my metal oxides. Metal oxides are basic. If you put them with water, so if you put sodium oxide with water, it will dissolve and react, and it will be fully dissociated. You'll make sodium hydroxide that will be fully dissociated. That means there's a lot of free hydroxide, so you've got a very, very high pH solution. It's similar with magnesium oxide, except this time it's sparingly soluble, and your magnesium hydroxide is also sparingly soluble, so there's very little dissociated. You've got a little bit, but not very much free hydroxide, so your pH of your solution is going to be much lower. It's much less alkali. You may be asked why these metal oxides are basic, and it's because of the oxide ion within them. That oxide ion is strongly basic. It reacts with water to form the hydroxide. So that is why your metal oxides are basic. It's because they've got this oxide ion that reacts with the water to make hydroxide. Looking at our sort of middle group, we've got aluminium oxide and silicon dioxide this time. They're a bit unusual. So aluminium oxide is completely insoluble because it's got a very high lattice enthalpy. And silicon dioxide is insoluble because of the really strong covalent bonds between all the atoms. So neither of these two are soluble. So we don't look at their reactions with water because they don't dissolve to do anything. Non-metal oxides then, these are acidic oxides. So your metal oxides are basic and your non-metal oxides are acidic. So let's take phosphorus pentoxide, P4O10 first. This shows the reaction, and it is very, very violent. So the P4O10 reacts violently with water and makes phosphoric acid, H3PO4. This is a very strong acid. It's also a triprotic acid. pH of that solution is going to be around 2. Now, phosphoric acid being triprotic, it can ionize once, and it can also ionize again. It'll ionize in stages to lose each of those protons one at a time. If we have a look at the structure of H3PO4, that is the displayed formula of H3PO4. You must be aware of that structure. So when it is fully ionized, it looks a little bit like this. But the reason it is such a strong acid is because those negative charges can be spread out across the whole molecule, which stabilizes it. It's like sharing the burden of those negative charges. So it actually spreads out across the whole phosphate ion, and that ion is tetrahedral. So the bonding electrons are spread out equally over all 4 bonds, and that is what stabilizes the ion and makes it so good at losing those H's that it had to start with. Looking at your sulfur oxides then. So we've got SO3 with water, that makes sulfuric acid as you know it. So H2SO4. That is a violent reaction, and you make your, as we know it, sulfuric acid with a pH of about 1. That's a diprotic strong acid. If you've got SO2, you will make another sort of version of sulfur acid where the sulfur is in a different oxidation state. So again, this SO2 is fairly soluble. It's not as violent like the first one. Your pH of your solution is a little bit higher because that acid is a little bit weaker. So it's a weaker acid. So your pH is going to be higher. You're going to have less free H+. looking at the structures of the two acids then, so you've got your displayed form of your sulfate ion on the left, and the reason that that is such a good acid is because, again, the charge is spread out across all of the bonds. So you can see there, rather than seeing it as two double bonds and then two negatively charged oxygens, it's spread out all over, and that stabilises that ion and makes it easy to lose the H's that it had. Similar for the sulfate ion, but it is smaller, so it can't stabilise the charge as much. So that is why it is weaker and less likely to lose its H. Okay, so we have established that when we put our metal oxides in water, we get basic solutions because of the free hydroxide. And the more soluble those oxides are, the higher your pH, because the more free hydroxide you will get. We also know that our non-metal oxides are acidic oxides, so they form acids when they react with water. And we've got silicon dioxide and aluminium oxide in the middle that don't dissolve, so they are essentially neutral. They don't react with water because they don't dissolve in it. So we've got our alkali oxides, our metal oxides, sodium oxide and magnesium oxide. There are alkali oxides. They will react with acids. Conversely, our non-metal oxides, which we know are acidic, will react with alkalis. So we need to have a look at those reactions. Let's start with our basic oxides then, our metal oxides, the sodium oxide and the magnesium oxide. So the sorts of reactions that they're going to undergo. So this is sodium oxide reacting with sulfuric acid to make sodium sulfate and water. So that is acid plus base giving salt and water. Same for magnesium oxide, but I've just used a different acid. So because I've used hydrochloric acid, the salt I will get is magnesium chloride. Again, that is just acid plus base giving salt and water. In the middle, we've got our insoluble oxides, the aluminium oxide and the silicon dioxide. Silicon dioxide will not react with anything, it's completely insoluble. However, aluminum oxide is amphoteric. That means it can react as both an acid and a base. So it will react with both acids and bases because it can be an acid or a base. You need to know examples of each of those. So you need to know an example of aluminium oxide reacting as an acid and one of it acting as a base. So this is the first one. This is aluminium oxide reacting with hydrochloric acid. So hopefully you'll realise that that means the aluminium oxide is a base in this example. And that will make aluminium chloride because that's a simple acid-base giving salt and water reaction. We also have aluminium oxide reacting with sodium hydroxide, and that is making this sodium aluminate. So that is with hot concentrated sodium hydroxide, and it makes sodium aluminate. So you need to know those two equations in case you are asked to give examples of aluminium acting as an acid and as a base. So they're the equations you need to learn for that. You also do need to remember what amphoteric means. You could be asked. That is a definition you've got to learn. Looking at our non-metal oxides then, so we'll start with the phosphorus pentoxide. So we know that the acid that makes is H3PO4, and we've therefore got the reaction of H3PO4 with an alkali. So rather than seeing, as we did before, the oxide reacting with the acid or base, it really is in this case the phosphoric acid that's reacting with the alkali. So we look at it slightly differently. So this time also we've got our triprotic acid, so we're going to react it one at a time. So here's the first. Then once you've made that NaH2PO4, you can react it with another molecule of NaOH, and that'll take off the next hydrogen, and then you can take off the third one. So you could see it stepwise, or we could put all that together and just have this reaction here showing the overall removal of all three of the H's from the phosphoric acid. The final one we need to know then is our sulfur oxide. So it's sulfur dioxide we're looking at, and that reacts with the base sodium hydroxide to make what is known as sodium hydrogen sulfate. The sodium hydrogen sulfate then reacts with another NaOH, and that makes us our sodium sulfate on the right here. So you need to know those equations as well. So you should be able to describe the reactions of sodium and magnesium with water. You should be able to state how elements sodium to sulfur react with oxygen, and then describe the physical properties of the oxides of sodium to sulfur and their reactions with water. And then finally, once they've reacted with water, you then need to describe their reactions as acids or as bases. Now, this is an awful lot of learning in this topic. There is a mind map for this topic that I would recommend you use, because otherwise it just feels overwhelming. So I'd get the mind map and use that to help you learn the bare bones of it, so you're not learning too much and it makes it much more broken down for you. So get hold of that mind map if you haven't already.